Hello, checking that I am online. So I'm back again with this idea to read the use the index look from Marcus Winand and try the examples on YugabyteDB. The reason for it is that this website and the book looks at many databases, especially there is Postgres, and then all the syntax is available and the same on YugabyteDB. But from performance point of view, being on a distributed database, some things may behave differently. So while I am reading to this and testing it on my lab database, I do this live and this is recorded. So if people prefer to watch it rather than trying themselves, it's easier to get back to it. So the previous ones which I've put on my YouTube, the previous one were about anatomy of the index, the where clause, how indexes behave with functions. We can create functions, index function, and then the index is used when the function is in the where clause, for example. And last week, I think we have seen parameterized queries, how it works, and I did a lot of comments about it because with Yugabyte, we are a bit different than with the databases which uses heap tables, because when you are doing the most efficient access, which is an index only scan, you don't really care about the cardinalities because anyway you are reading just a range, and that's the best plan. Of course, if you read really all rows, it's a bit faster with a sequential scan, but a range scan is not a problem with an index organized table like we have on the primary key there. So that was about parameterized queries. And now there are many chapters about searching for ranges. So by default, and I will go to my demo screen to see where I am. I've quickly rerun again everything I did the last week, so probably we are in the same state. I have a table, employees. Let's see the definition I have for it. Primary key is subsidiary and employee. So we have seen that before. Adding a kind of multi-tenancy to the data model was done by adding a subsidiary ID in front of each primary key. This being hashed means that if I have many users working on different subsidiaries, this will be distributed over the distributed database or the YugabyteDB. And then the second column is ascending, which means a range. So if I query for one subsidiary ID, I go directly to one tablet, and in there the employees are sorted in order, which can be good or not. The advantage is that I can query on ranges of employees, and we have created a few indexes before, one on a function with the age, and I think I mentioned that this one is not a really good idea because the age can change, so I had to fake it and to tell the database that this is a deterministic function, but it is not. Let me drop it. Drop index covering. Was just to show the error we have when we do this kind of thing. I had an index on last name, which is ascending on the last name. So that means range sharding. The idea is that we may have queries for all names starting with a letter, for example, and you need a range for that. We have another on subsidiary, last name, first name, phone number, and another one with a function. So this function is deterministic upper. Okay, so this is what I have. I guess I'm in the same state as expected by this page, but we will see it. So inequalities are those predicates where you don't look for a colon equal a value, but a range. So greater than a value, less than a value, or between, which is like greater or equal to the first value and less or equal than the second one. So those one can use an index, and this doesn't precise that the index must be a range sharded, because those pages are about monolithic databases where you have bit trees. So we don't have bit trees in Yugabyte, we have LSM trees, and they are first sharded. So this is true if we are on a range index. If the first column is a hash, then that breaks the range, because the goal is to distribute. Even a like filter can, under certain circumstances, use an index. We have seen that before, because the Postgres query layer will transform, for example, if you say all names like F%, so starting with a F, the query planner will add a predicate greater or equal than F and less than the next selector. G. Using this option limit the choice of the colon order in multi-colon indexes. So when you have an inequality, you go directly to a value, but when you have a range, you need to think about it. Usually, you will put first the columns where you have equalities, because they can be used and sharded, and next the range. This limitation can even rule out all optimal indexing option. There are queries where you simply cannot define a correct column order at all. So first one about those greater, less, and between. The biggest performance risk of an index range scan is the leaf node traversal. In a bit tree, you go through the branches to the first leaf, and then you read the leaf block. In a block, so I'm talking about databases with B-tree. There, it is different in distributed databases. With B-tree, you read a block where you may have 10, 100,000 entries there. But if your range is very wide, you may have to read other leaves. So the B-tree has also links between the leaves, so that when you read one, you don't have to go to the upper branch to go to the next one. You have directly a link to it. So you can read multiple blocks that are logically adjacent on the value, but probably physically scattered on the disk. With YugabyteDB, we don't care about that, because we don't have bit trees. We store everything in LSM trees, which are sorted and maintained sorted, so that you don't have to follow blocks. We don't have blocks actually, because it's not easy to distribute blocks. If you work on blocks, then you need to access to the whole block, and then two sessions on two different nodes may have to exchange the blocks. So we don't use blocks. We directly work with key values, the index entries. So we will see how the remarks here are different for Yugabyte. But this remains the most important when you have an index scan. You must think about your index in a sorted structure where you start and where you end. So basically the access will be seek into the start and then read until the end. So this is a query with a parameter with a range on date of birth. For this to be efficient, first, do I need an index? Depends on the range on date of birth. If my range covers 1 century, then probably I will read all employees and I don't really need an index. But if my range covers 1 year out of 100, then maybe an index range can be interesting, and then an index on date of birth. I don't think I have one, but we will see if it's created later. So index on date of birth, start and stop condition. If I add, yeah, that's the important point. If I add the subsidiary, yeah, let's see. I will run this query. So this is using parameters here. We will do same kind of thing, except that it's not exactly the same syntax. I will check if we have the syntax for Postgres. If not, I will do it. That's easy to translate. Are we still on the where clause? I think so. Concatenated keys, we have seen that. Functions, we have seen that. Partial indexes. Did we see the function indexes? With date of birth. Function, yeah, was not there. Okay, I will come back to this. So I run this query. First, I will translate it to a Postgres syntax. And I will use the Juke translator for that. This is an Oracle syntax which I want to transform to Postgres or YugabyteDB. And the first one was without the subsidiary. So we'll put the subsidiary later. So that's the query I want to run. So select from employees where date of birth, no. Okay, I will do something else. I changed my mind. Instead of converting it. Anyway, I don't really need the to date, but instead of converting it, I will show another way to use the Oracle syntax in Postgres and in Yugabyte. So let's say I want 19 other 1 month. So from the 1st February 1971 to end of February let's try 29. I don't think it was a bit sextile, but I want to see if I have an error. And for the moment, I will not put a subsidiary. So that's the query I want to run, except that this is numerical syntax. And I didn't replace the right thing I wanted to replace. This is not the way I put dates. I use the literal date. But I also like to test different things. Okay. So toDate is running in Postgres. 29 wasn't existing. I'm surprised about. Ah, yeah. Okay, learn that today. I didn't know that toDate works like that in Postgres as well. And then Juke was right in the translation. Cool. So I have nothing there, but I don't really care because I want to see the execution plan. I see a question in the chat about the best place to learn SQL. Yeah, come here. we can learn SQL. SQL.ru is like it. I don't know. For me, really, the best way is probably to start with Marcus Winand, the website, the book. That's probably the best way. And let me show you something else if you want. Just to show you what we have done in Yugabyte. If I go to the cloud, Yugabyte. So this is the Yugabyte cloud where we have a free tier. I think I have the free tier because here I have multiple accounts. Yeah, free tier. And I will show you. You can create a database in the Oracle free tier. That's quite easy. You just have to put your email. No need for any credit card. I have something that is a bit long in my browser, but it will come quickly. The nice thing is that we have a cloud shell, so we can connect directly to the database from the shell, from the browser, I mean. I put the password that I have defined when I've created my free database. And this is to answer to Clap Slack about how to learn SQL. If you want to learn SQL in 60 seconds, I think that's a bit optimistic. But in our Cloud Shell, we have some examples where you just click and you see the commands, which gives you an idea of the things easy or complex that you can do in SQL. And if you have questions, ask me. Do not hesitate. You have my my email, my blog, my Twitter. You have a lot of things. So the idea what we have put in this Cloud Shell is a tutorial where I can copy and run, and I can also run things manually in there. That's the beauty of it. So this has created a table depth. And you have very small sample tables, department, employee, famous one, made famous by Oracle, but it existed before in the first papers about SQL. and you insert some data. Duplicate key, probably I already created them. Yeah. I dropped them to recreate them because I don't know exactly what I've tested there. Hey, you speak French. So do not hesitate if you have questions on this. I'm just showing the Cloud Shell to make it easy. Did I create it multiple times? Okay. And then when you have created the data, the idea is that in this tutorial, you have a few examples which I think is good to start to understand SQL, and we explain it. And if you have remarks, feedbacks, or anything about it, please tell me. We can change them for. So the first one is for me is the most beautiful SQL queries. The reason is history. In the first papers about the SQL language, this was the first example. If you have a data set with employees and their managers and their salaries, like we have in this table, select star from amp. So we have employee ID, we have pointer to the manager there, if there is a manager. Of course, there is a president with no manager, and the salary. And a query like, give me it was not the same one. This one is yeah, this is not the one I was thinking about. I was thinking about a query that's that quickly queries which employee has a higher salary than the manager. Maybe we'll see that after the update. So this update is something quite easy, adding increasing the salary, except for this kind of job. And this looks easy to do, but if you want to code the same, it's not so easy. The big advantage with SQL is that what runs there with one query will still run with multiple users doing the same thing at the same time, and will always be consistent. This is the example I was talking about. List all employees earning more than their manager. And this is a join because you read employees as employees and the employee table as the managers. And you link them by saying the employees as employees, their manager is the managers, the employees as managers, employee number. So this is a very quick query that tells you which one has a manager salary that is less than employee salary. So there are some examples also to give some best practices, like using prepare statement, like where you prepare a statement with a parameter, and then you call it with different parameters, exactly the same as you compile a program or procedure, and then you run it. There are also some things about indexes there, where we just create a table and we create an index on it, and also to give you analysis in beta in the version that I have, and also to give you the best practice, like when you query on your small development data set, always check that the execution plan is what you expect. Index only scan. That's the best access path we can have. Okay, so all that in the cloud, Yugabyte cloud. I wanted to put that in the chat, but if someone wants to create a free database there. Okay, so let's go back to use the index there. And here, what I was doing was looking at the execution plan without index. Even if I query just a small part of my data, the employees born in February 1971, this has to scan all employees. And this is where we want to create an index, create index. Let's call it employee date of birth on employees. So I want the index to be sorted on the date of birth to be able to seek to the start and read them. Ascending or descending, but we need a range. If we had a hash function on it, will not work. And this, I expect an index scan, not an index only scan, because I'm reading some columns that are not in the index. So I expect, let's running, I expect an index scan that goes directly to the first value and then read until the end. I add a function execute snap table. So this is a small utility I've built before, where I snap reset the statistics. Just give me an idea of the activity in the distributed storage. So behind this index scan, this went directly to one tablet, directly to one place. And because I have no employees in this range, nothing to read more. Okay, and so the idea here was to show the start-stop condition. And if we add the subsidiary ID there in the query, so this is where I add a subsidiary, let's say 1. I don't even know if there are some of them. But if I explain plan for that, hey, that's interesting. Cool. So this is some place where it differs from what is written there. I think so. The idea there is to tell you that because you want a range, but for a specific subsidiary, you want an index where you can put the subsidiary in front of it. But for this is not mandatory. This will just mean that you will read all employees in this range, and maybe you have more than what you want, and later they will be filtered on the subsidiary, which is okay if the cardinality for the subsidiary is not too large. But in this kind of schema, what you expect, drop index, this kind of schema like multi-tenancy, where probably each user will query on one subsidiary only, then probably you want to put the subsidiary ID in the index, and in front of it, hash it in Yugabyte. So it will be the default, but I put it explicitly. We'll see the same in the execution plan, except that there is not this filter afterwards. You see index scan, so that's the same. But now the filtering on the subsidiary ID is pushed down to the index range access directly. So it goes to the right tablet for this and then goes to the range, and we don't see this filter afterwards. Okay, and so what was mentioned there, keeping in mind that this was written for monolithic databases with bit trees. So, but same idea, index still used, but of course the ideal index has to cover both columns. So this is what I did. And this is really something that is good to look at and understand in Marcus Winant's publications or conferences, trying to understand visually what is done by the index. You don't really care about the structure of the tree or any different structure. The most important is that the index is stored, a sorted structure. So the B tree is sorted, the LSM tree is by definition also sorted. So you go to the first place. So Marcus was not looking at February 71, but January 71. And has read all that until the end. So this is an index starting with the date of birth and the subsidiary at the end. So the opposite of what I did before. And that's okay here because we go to a range and then we have the subsidiary, but we still read entries that belongs to different subsidiaries. So we filter them in the index access, but later. This is the diagram with subsidiary in front of it, as I did it. There you go directly to the subsidiary, and then within the subsidiary to the range, and there you have only those with the same subsidiary. So Marcus here queried on 27, and then all the 27s are at the same place. So that's better. And that's even more better in a distributed database because this first column can be used to hash and to distribute. So that's basically what was written there. Just looking, but this is what I mentioned there mostly. Huh? Okay, and what was next there? The difference is the equal operator limits the first index column. Exactly what we have seen, even if it's not the tree, it's the same idea. Rule of thumb, index for equality first, then for range. So the most common indexes you will find in all databases, but more in distributed like Yugabyte, they will start with columns where you do only equality. And then you will probably hash it. So you distribute your data, you distribute your load, you distribute your access. And then the columns on which you range, you have them in a range. For some columns, it's quite easy to guess that you will have only equality. For example, if you have an ID that is generated, the order has no business meaning because it's just generated to have unique numbers. So subsidiary ID, employee ID, you probably don't query them on a range. Even if you think that employee ID will give you an idea about the date of arrival, better to query on the date of arrival if you have it in the table. Other data types, you can guess that you will have range queries on them. For example, a date. With a date, you will probably have queries asking for a range of dates for 2 consecutive dates, for a week, for a month at some point. So when you have a date, probably think about range queries on them. Texts, really depends what you put in a text. If it's a text where you think the alphabetical order has a meaning, and you will query with patterns with a starting point, so starting letters, then probably you want a range on it. If the text is a UID stored as text, which is not a good idea, but let's say that probably you will not query an range on it. So the actual performance difference depends on the data and search criteria. The difference can be negligible if the filter on date of birth is very selective on its own. The bigger the date range becomes, the bigger the performance difference will be. And this is where the query planner, the optimizer, will try to estimate the selectivity of the different columns to know which index is useful. So if you have many indexes, you can use efficiently one to access your data, and then the query planner will try to use the best one. My recommendation is not to create too many indexes, not only for the overhead on modification on data, but also the more indexes you put, the more risk of choosing a bad index with the query planner will come. So create only the indexes where you know it makes sense on the data for some queries. In this case, where you have something like multi-tenancy or subsidiary ID, I guess that most of query will have the subsidiary ID. So you query for your subsidiary, and maybe there are some reportings other multiple subsidiaries, but reporting will probably scan a lot of data. But the OLTP queries will have the subsidiary, and then you should find it in front of the primary key and in front of a lot of indexes, except if the other columns are selective enough and maybe you don't need it. But anyway, why not putting it? And those are examples of execution plans. We have seen the Yugabyte one, which is the same as Postgres. In Oracle, you see the index range scan with the access to the table. This is the same as an index scan. It's only when you have index only scan that you have only the index access. So that's for Postgres. And this is a secondary index, so it's the same for Yugabyte. In Yugabyte, only the index scan on the primary key doesn't have to go to the table because the primary key is the table. DB2 SQL Server, I don't really work with them anymore. But same idea, those are bit trees, so displayed differently, but the same concepts. The predicate information for the index range scan gives the crucial int. So always look at the execution plan and the index condition in it that you find there. Of course, you may guess it from your query, but in your query, it can be a bit more complex. You have functions, you have modifications, so you don't really know if what you think is a range in your query is actually a range when accessing data. With the query planner, you know it because you see the access. You know that index condition is used to access data. The execution plan was simplified for clarity. I don't see exactly what was simplified there, but no problem. The conditions on date of birth are the only one listed as access predicates. They limit the scan index range. The date of birth is therefore the first column in the index. The subsidiary column is used only as a filter. So this shows a plan with the filter, except that I do not see it there. subsidiary colon is used as a filter was the case in my example before with the previous index, when I had the index only on date of birth, subsidiary was the filter. I don't really see it in this page. Database can use all conditions that access predicate. I will check it again, but is this something wrong in this page and expected filter? Let's look at the Oracle one. Filter and access. I think something is wrong there. Let's look at the first one, where we have a filter on end date, so that's even different in this condition. I'm not really sure which query is there. This does an index range scan on AMP test with access on the range and filter on subsidiary ID. Okay, so this one was when Marcus created an index starting with date of birth and then at the end subsidiary. So the date of birth was really used to access to the index and then add to filter subsidiary, but without using the index structure for it. And then the other index with subsidiary in front of it was used fully to access to subsidiary. So yeah, there are no errors there. It just shows the execution plan related to those two diagrams. And that's interesting because if we compare with Postgres, we don't see this information. Oracle tells you date of birth was the access, subsidiary was a filter. But Postgres doesn't tell you that subsidiary was a filter. It's put in the index condition because this colon is in the index. It's not used to access, but it is still run when accessing to the index. Postgres says filter only when it is filtered after accessing the index and the table and filtered later. So I guess, for example, that in those two cases, the Postgres plan doesn't show a difference. Let me put that in a notepad to compare exactly and be sure that I'm not misleading. So this is the plan for Postgres when subsidiary is at the end of the index, and this is the plan when it is at the beginning. And I see a difference in the width, which I don't really understand. We see the order there. That is different. But that's interesting. If you come from Oracle, you are used to differentiate access and filter, and here with Postgres, it's a bit more subtle because you need to know the structure of the index to understand that here this was filtered afterwards. Let me check again here. So that was what I had with everything in index condition. I will add verbose here. Where we see the output, but we don't see more information, and I will explain. Yeah, we will not see difference. Yeah. So that's something that can be a bit misleading, because we can see filter in a Postgres plan, but filter is different. Filter is really after the operation, where for Oracle it says filter when also when it is filtered within the index. In summary, good to look at the execution plan, but very important to understand the structure of the index. Of course, looking at execution statistics, we can see the difference. Maybe I can just do it in the same way I did it there. So here I have an index on employees, then birth date. And yeah, I have no data here. I want data, so I select employee. Let me check if I can insert more data. We had a function there. Date, random, okay. Okay, I don't waste time in putting more data there, but I want to just to show that between those two indexes, there is a difference in the performance, because this can be used by my query. This will be used, but not for subsidiary, just later. And with Postgres and with Yugabyte, we don't see the difference in the execution plan. We can see the difference in the performance if there are a lot of subsidiaries. Okay, going to the next page there. I will try to cover the others quickly, because I have a raw idea of what we have, and I think we already have seen that. So should I put my YouTube channel in the chat so that everybody can see it? YouTube, my channel is my name is Frank Pachot, so that's quite easy to find. Where is my channel? YouTube, your channel. I've put all that in a playlist, and again, what I'm streaming today, I will put it there in this playlist. So I have a few hours just reading, use the index look, and testing as I did, and doing a lot of different things in between. So the like, we already have seen that if you have a query, now here you have a lot of things. You have an upper function, and we have seen that this is okay if I create the index on upper last name, because what counts in the index is the final value that is indexed. And a like with something before the joker, the pattern, the wildcard, this can be used for a range because this is the same as starting with a win and going further. So the Postgres plan shows this as at the end, we have a filter with exactly the predicate that has been put. The like is just transformed in a different syntax, but that's a like. But in order to reduce the scope from the beginning, from the index access, the query planner has generated a higher than, less than, depending on the alphabetical order defined there. For Postgres, you might need to specify an operator to use like expression as access predicate, so that's more complex. Postgres and Yugabyte may have extensions with other data types, and then when you define a new data type, you define how it behaves with patterns. So this is the idea. If you say like and you have two letters, then it goes to a range with many entries, but at least you go to that range, and then this range is scanned to filter later. If you have three letters, then the range is more narrow, and with more letters, it goes directly. So again, it's a question of selectivity. This is what is written there. But be careful, if you put a percent in front of it, then it cannot be a range scan. I've seen that was in an Oracle database, but works the same. I've seen that where the users complain about slow queries. It was a watchmaker. I live in Switzerland and I've been doing consulting in Switzerland, and there are a lot of companies making watches there. And so finally, the slowness, the easiest thing to do when you can is go just with the user and look at what he's doing on his screen. And what I've seen is that he was taking the watch that they had to repair, and the idea was to enter the serial number of the watch in the GUI to find it. And I've seen that he had the serial number on the watch, but put a percent in front of it. And then I understood this cannot be a range scan. It has to scan everything because the wildcard was at the beginning. And I asked the user, but why do you do that? And just says, because it happens sometimes that the first letter is not easy to read and we don't put it, and just by habit is doing that. And when I explained him that that's okay if they really don't know the first number, but if they are sure that they know the first number, better not put the wildcard as the prefix, and then everything is faster, and this was faster for 99% of their usage. And this is just because I know how it works. I know how the index is in there. The user just doesn't know, because when you query something on Google, you don't really think about those kind of things, for example. Really depends on how this is indexed. So that's really important to understand the like pattern with a wildcard in front or not. The opposite is possible. A like expression that starts with a wildcard cannot serve as an access predicate. Well, there are also some possibilities to do that. For example, in Postgres, we have an extension that can index some trigrams. I will show an example I have in a blog post. If I search on dev2, I have a blog post on text search which I wrote when we introduced gene indexes, inverted indexes. They exist in Postgres, but for Yugabyte we had to implement it a bit differently because the storage is different. And at the end, I think I've added it when someone told me on Twitter, asked me on Twitter, does it work with the trigram? And yeah, that's easy. You create the extension pgtrgm, and then you can create an index like this. Whoops. So I add a colon name, and I've created an index on name with the operation trigram, which means that it will take the name, take all trigrams, so consecutive 3 letters, index that. And then with this, you can index something with a like. Want to do that on the first name there? So here I have first names that are random. Okay. If I explain, let me check which indexes I have. I have an index on last name, even on umper, but I will take just last name. If I explain, I put cost off to have the plan not too wide. Cost off, analyze, select star from employees where last name. So let's do the first thing, starting with F. Starting with F was filtered for everything between F and G, return 400 rows. That was an index scan, reading only 400 rows out of 10,000, I think. If I query ending with F, or if I put a wildcard in front of it, that cannot use an index, so it's sequential scan. And I have 10,000 of rows, so 8,000 were removed to return those. Let me find this one. So I want this one. Let's say I want this one, so this returns 0 row, expected 1. If I narrow it, yeah, that was the first name, last name. Okay, I will pick one that I find nice. Il vaut. Is that nice? Yeah. So this is a query that returns 1 row only, but I had to do a sexcon and remove most of the rows because I start with a wildcard. And let's say I start with a wildcard because I don't know those two first ones. So this returns 2 rows, but I don't know. And this is where I create extension extension pgtrgm extension. And then I can create index last amp last name trigram on employees using Gin on last name with this trigram operator. So this creates the index, and now the same execution plan is using this index. This is really cool. If you come from Oracle, there are no easy way to do that. And you see that the case I mentioned with the serial number of the watches in Postgres, that's something where I can use this kind of index. Trigram, why 3 letters? Because it's enough to find to find interesting rows and not too much to index. So this is really interesting. I have 3 letters in a name. I can still use an index, even if I don't know if those 3 letters are at the beginning or the end. Really cool feature. And I didn't install anything. I just create extension. Why do we have to create extension? Just because extensions come on top of Postgres and then have specific names for function, and just to be sure that they do not collide, but there is no problem to do that. I created the extension, I created this index, and if I look at employees structure, I should see my index there. So I created using Gin. Internally, it is YB because the YB, the Yugabyte implementation of it, is a bit different. So that's something you don't find, at least at this place, in used index Luke, mostly because this is specific to Postgres. Probably it is mentioned later for full text. For Postgres database, the problem is different because Postgres assumes there is a leading wildcard when using bind parameters. So yeah, that's a point about parameters. If you use a parameter, then in Oracle, then the plan will be set before knowing the value, and then the plan will be determined before knowing if there is a wildcard in front of it or not. And this is because Oracle tries to share the plans and not to reparse, re-optimize each query, which is good for the queries that are always the same. But in this case, the default Postgres use a custom plan for that. Think about it. How can you index like search that has only one wildcard at the beginning of the search term? So we have seen the trigrams. That's easy. And there is also the possibility, for example, I don't even know if we have it in Postgres, but for example, let me show something on Oracle just for the fun of it. In Oracle, there is a reverse function. I will check if it's also in Postgres. I'm not sure. if I reverse Frank, I have if Oracle I need from door. So it reverse it. So I guess that something like %xy can be written as something like reverse, and I can index on reverse. So I think this is the answer to the question. Let's see if select reverse. I don't know if it's standard SQL. Of course, everything exists on Postgres and Yugabyte. So that can be a possibility also, using reverse and views to hide it, and creating a function index to index this kind of thing if we need it. I think I will continue for something like 20 minutes. I'm going slowly reading that because I'm going in many different ways, but I think it's important also to see all the different aspects of it. Index merge. Oh yeah, that's. Let me look at an execution plan. I don't see it here. So it is one of the most common questions about indexing. Is it better to create one index for each column or a single index for all columns of a where clause? The answer is very simple. In most cases, one index with multiple columns is better. That is a concatenated index or compound index in concatenated index. The reason for that is that even if there are workarounds around it, usually you have one way to access data and then use one index. If you have a query on upper last name and date of birth, if you have an index on upper last name and another index on date of birth, the first thing the query planner, the optimizer, will try to do is look at the selectivity and see if one index is selective enough to be sufficient. So upper last name less than a value, depend on the value. Date of birth less than a value, depend on the value. So even the estimation of it is not really easy. So the best for that is to have an index with multiple columns, the most selective first, because it is a range here, an inequality, and then the other to be able to filter. If you have two different indexes, the different databases have different ways to optimize it. And this can go through bitmaps. For example, Postgres will read this index, and rather than going to the table, the heap table, to get all rows, it will just build a bitmap of not the rows but the blocks in the table, and then do the same with the other index. And two bitmaps are easy to merge with an AND operation. And the expectation is that the merge of it will reduce the number of blocks to read, and then it goes to the table to read them. So this is something where you will see in Postgres. I've not seen those there, but in Postgres you will see bitmap scans. You will not see that in Yugabyte for the simple reason that bitmap scans, the bitmap is about blocks, and as I mentioned at the beginning, with a distributed database, we do not read blocks to read rows in it later because this doesn't scale. We read values keys and range of keys, and then you don't have this. And also in many cases, you don't really need it, because this is really useful for heap tables. When you go from an index to from the primary key index, for example, to the table, then you want to reduce this random reads, which we don't have when we range scan from primary key index. From a secondary index in Yugabyte, you still have to go to the table later, and then you will try to have the best secondary index for it, and the best secondary index will have at least those two columns in the index. Maybe one, the most selective, as the index key, and the other with an include to get a covering index, at least to filter most of the rows before going to the table, even if you have to go to the table later. So this page explains the combination of indexes, which is like a join. And yeah, that's used in data warehouses. And for example, in Oracle, you have this kind of plan, but building bitmaps at runtime is expensive. And with Oracle, you can create bitmap indexes. So you directly store the bitmap that maps to the rows in the table, and they can be used and merged. Why for data warehouses? Because, as I mentioned, the bitmaps work with blocks, and a bitmap will address multiple rows, and then you have problems where when you have to lock an entry, you have to lock multiple rows, and this doesn't scale with OLTP. This is why Marcus Winant says bitmap indexes are almost unusable for online transaction processing. This is only for data warehouse where you bulk load, then you build your bitmap indexes, and the advantage is that you don't have to build them at runtime. We don't have this in Yugabyte. For those cases, create indexes, create material as use. And probably I will go through the partial indexes. Maybe not next week, because next week I'm going to KubeCon in Spain, so probably the week after. Anyway, about partial indexes, I've also done. So let me show you YouTube. This is my channel. So you can find it with my name, Franck Pachot. And I've done also some videos on, well, I think I also referenced it from a playlist. Not there, not there, not there. Let me search Yugabyte. In the Yugabyte YouTube channel, every Friday we do the YFTT, the YugabyteDB Friday Tech Talks. And if you look at the playlist, I've done 2 about indexes. All the topics are interesting, but here I was mentioning indexes. So this one, indexes in Yugabyte, and I did another one on partial indexes and expressions. So that's also something if you like to watch videos where I do small demos exactly the same as I'm doing there. The difference is that here I'm in total improvisation while reading this, and the YFTT are a bit more prepared. Okay, so next week I will not Twitch. Probably the week after we will look at what is mentioned in partial indexes, and nulls in database will be also interesting. Let me just put this in my file there. to remember where we are. And yeah, that's all for today. I think it's interesting to look at it, and if you like to watch videos, but most important, this website and the book are really interesting and will be useful even if you use databases, different databases like Yugabyte without bitry indexes. The goal is understanding. I will compare this with school, for example. My kids are often telling me, but what we are learning at school is not really useful because we are doing things in maths that I will not do later. And first, you don't know, but most important, that at school you don't learn things. You learn how to think about things and understand them. And it's the same here. If you understand bitry indexes, you will understand all databases. Okay, stopping the Twitch there, and I will put the recording on YouTube and see you in 2 weeks. Bye.